Among the many ideas proposed to resolve the mystery of why we see no signs of advanced alien civilizations in the universe, one stands out for its quiet elegance and its radically inward focus. This theory, known as the developmental singularity hypothesis, challenges the long-standing assumption that progress among intelligent species must inevitably lead outward, toward galactic colonization and visible interstellar empires. Instead, it suggests the opposite, that sufficiently advanced civilizations tend to move inward, toward increasing complexity, density, and efficiency, until they become virtually undetectable to the rest of the universe. Rather than aiming to dominate external space, they compress their existence into inner domains so optimized and miniature that their outward footprint disappears entirely. The developmental singularity hypothesis stems from a broader framework in evolutionary and developmental systems thinking. At its core lies the observation that many systems, both biological and technological, do not simply evolve in one direction of growth or expansion. Instead, they follow a developmental trajectory marked by increasing specialization, integration, and internal coherence. Just as a human embryo grows into a complex organism by differentiating its cells, optimizing its energy usage, and refining its internal systems, a civilization might evolve by reducing waste, increasing intelligence, and concentrating its capabilities into ever smaller and more efficient structures. This inward trajectory has been referred to as space-time energy-matter compression. In this process, as civilizations become more intelligent, their use of space becomes more compact, their interactions with time become faster and more deliberate, their energy usage becomes more refined, and their relationship with matter becomes increasingly optimized. The overall result is not a sprawling expansion across the stars, but a kind of implosion into highly concentrated forms of intelligence and computation. Such civilizations, the hypothesis suggests, do not build empires across galaxies, but rather create digital or quantum environments of immense power and sophistication, hosted within microstructures that may be no larger than a small celestial body or perhaps even smaller. One of the most provocative extensions of this theory is the idea that black holes may represent a natural developmental endpoint for advanced civilizations. Black holes are the most compact and efficient structures in the known universe. They offer the highest energy densities, the greatest time dilation effects, and potentially the richest platforms for computation, at least theoretically. Some theorists have speculated that black holes might be not only astrophysical phenomena, but artificial constructs engineered by advanced intelligences for the purpose of ultra-dense computation, information storage, or even universe replication. This idea may seem far-fetched, but it serves to illustrate the radical compression of scale and function envisioned by the developmental singularity hypothesis. The implications of this hypothesis are deeply tied to the so-called Fermi paradox, the question of why, in a universe that appears so hospitable to life, we do not see clear evidence of other intelligent beings. If civilizations tend to grow, expand, and colonize, we would expect the galaxy to be teeming with signs of them, radio transmissions, artificial satellites, megastructures, or at the very least some form of astroengineering on a cosmic scale. Yet our telescopes return only silence. The developmental singularity hypothesis proposes that we see nothing because advanced civilizations are not broadcasting, not colonizing, and not building in ways that leave detectable traces. They are busy refining themselves into ever smaller domains, turning inward rather than outward, and in doing so, becoming invisible. This idea stands in sharp contrast to popular visions of the future, which tend to imagine humanity spreading across planets, building cities among the stars, and constructing interstellar networks. These visions assume that progress equals expansion. But if the developmental singularity hypothesis is correct, this might be a misunderstanding of what true advancement looks like. Instead of sprawling out, intelligent civilizations might choose to refine, to miniaturize, and to fold their complexity inward, seeking perfection of form and function rather than dominion over space. Biological analogies help illustrate this pattern. Consider the way in which a developing organism becomes increasingly complex even as it grows more compact. A fertilized egg divides and differentiates, forming organs and systems that become more integrated and capable, even though they do not expand without limit. Or take the brain itself, a compact mass of neurons capable of astonishing feats of information processing, far more efficient than any supercomputer. Nature often privileges compactness, coherence, and efficiency over size and volume. The developmental singularity hypothesis suggests that the same principle might apply to civilizations on a cosmic scale. Another way to understand this hypothesis is to view civilization as a form of intelligence trying to maximize its control over its own environment. In the early stages, this may involve manipulating the natural world, developing agriculture, building cities, and eventually exploring space. But once a civilization reaches a certain threshold, the path to further advancement might lie not in expansion but in refinement. Mastery over matter, energy, and information allows such a civilization to create internal environments more rich and meaningful than anything the external universe can offer. These internal environments might take the form of simulated realities, quantum substrates, or engineered worlds that exist entirely within compressed domains. At this point, the motivations of such a civilization shift. Why send ships to distant stars, which takes thousands or even millions of years, when an entire cosmos can be simulated internally at a fraction of the energy cost and at speeds vastly greater than those allowed by physical travel? Why expose oneself to the randomness of cosmic events when one can design perfectly stable and responsive environments inside artificial matrices? The inward turn becomes not a retreat, but a leap forward, a path toward godlike control over experience, thought, and existence itself. This vision also transforms our understanding of what it means for a civilization to be advanced. Traditionally, we measure advancement by technological artifacts, physical infrastructure, and ability to alter the external world. But under the developmental singularity model, advancement may be better measured by efficiency, miniaturization, integration, and inner richness. A highly advanced civilization might be one that has eliminated all waste, created perfect feedback systems, and concentrated its activity into a tiny, silent core. Such a civilization could have vastly outpaced our own in intelligence and capability, yet leave no visible sign of its presence. This leads to a powerful reinterpretation of the search for extraterrestrial intelligence. If most advanced civilizations follow this inward path, then our efforts to detect them using radio waves, telescope surveys, or searches for alien megastructures may be fundamentally flawed. We may be looking for the wrong signatures in the wrong places. Instead of looking for expansion, we should be looking for compression. Instead of vast stellar engineering, we might do better to seek anomalies in black holes, time distortions, or unexplained concentrations of information in very small regions. These are speculative pursuits, but they match the logic of the hypothesis. One of the most fascinating elements of the developmental singularity hypothesis is that it mirrors trends already observable in human society. As our own civilization has advanced, we have seen a dramatic shift toward digital miniaturization. Computers once filled entire rooms, now they fit in the palm of the hand. Communication networks once required massive infrastructure, now they rely on microscopic semiconductors. Entertainment, once experienced in physical theaters or arenas, now unfolds in personal virtual spaces. Even our ambitions for exploration have shifted. The idea of simulating a planetary ecosystem in a lab or constructing digital worlds through artificial realities now seems more achievable than colonizing Mars or traveling to another star. This suggests that we, too, may be on the path of inward development. As our technologies improve, we may increasingly choose to focus our efforts on perfecting digital environments, mastering biological interfaces, and creating compact systems of enormous complexity. The ultimate trajectory might be toward the construction of controlled, inward spaces that offer everything once sought in the stars, but at a fraction of the cost and with vastly more precision. The future of humanity, under this model, may not lie in the stars, but within the atoms and circuits we learn to shape. Philosophically, the hypothesis opens up profound questions about purpose, destiny, and the meaning of advancement. If the highest state of development is not to conquer but to comprehend and perfect, then the ultimate goal of civilization might be inward harmony rather than outward conquest. This vision aligns with spiritual traditions that have long emphasized inward journeying as the path to truth. Whether in meditation, philosophy, or science, the idea of turning inward to find deeper order has a long lineage. The developmental singularity hypothesis brings this theme into the realm of cosmic evolution, suggesting that perhaps the universe itself favors inward refinement over outward expansion. Yet, the hypothesis is not without critics. Some argue that it underestimates the drive for exploration, that it ignores the possibility of simultaneous inward and outward growth, or that it makes assumptions about the goals and psychology of alien minds. Others question the feasibility of total inward compression, pointing out the technical and physical limitations of computation at ultra-small scales. Still, the hypothesis does not claim to describe every civilization, only the dominant pattern for those that reach a certain level of advancement. It allows for exceptions and acknowledges uncertainty, but offers a compelling narrative that fits both the silence we observe and the trajectory we ourselves seem to be following. In practical terms, the developmental singularity hypothesis advises caution in our expectations about extraterrestrial life. If we expect to find advanced civilizations by looking for sprawling space empires, we may be forever disappointed. The silence of the stars may not be an absence of intelligence, but a sign of maturity. We may be like children shouting into the void, unaware that the wise have long since moved beyond shouting, beyond space, beyond even time as we understand it.